So the biggest takeaway in this first part of this section is knowing how to find the domain of the sum, difference, product, and quotient. And for the sum, difference, and product, the domain of the function is the intersection of the domains of the two original functions. For the quotient, you have the added restriction that the denominator function has to have all the x values removed that make it equal to 0. So it's still the intersection of the two original domains with the added provision that g of x, the denominator function, cannot equal 0. So it's helpful to think of functions as sort of machines that take an input and do certain algebraic manipulations and produce an output. And it's especially helpful to think of them that way when you have one function, like this one, followed immediately by another function, using the output of the first function as the input of the second function. And so here we have a diagram that illustrates this one function followed by another. So the input here is x, and that goes into the function g, and then what g does is it squares x and then adds 1. Now you're going to take that result, x squared plus 1, and throw it into the function f, and what f does is takes the square root. So the square root of x squared plus 1 is the ultimate output of this particular sequence of operations. And so what we have here is two functions, the first being, or one of them being the square root function, and the other one being this function that squares and then adds 1. And what we did was f of g of x. So that is what we mean by composition of functions. So if you have any two functions and start with a number x in the domain of the first function, say g, and find its image, g of x, and then take that number, g of x, which may or may not be in the domain of f, but if it is, we can then calculate the value f of g of x. This new function h, which is the function f of g of x, that's obtained by substituting g into f, is called the composition or composite of f and g, and the notation is with this little open circle. And so we can do more fun kinds of things now with functions, because now we have another operation that works with functions, and that's called the composition of functions. And so here we have this example where our first function f of x is 3x minus 5, our second function is g of x, 2 minus x squared, and we do these two calculations. First, f of g of 0. In order to do that, you first have to calculate g of 0. So g of 0 means go to the function g and substitute 0 wherever you see x, and that's going to give you 2, because g is 2 minus x squared. Now you want to do f of that value, so you need to do f of 2. f of 2 means go to the function f, and wherever you see the variable, substitute the number 2. Here's the function f. If you substitute 2 where x is, you'll get 3 times 2, which is 6, minus 5, which is 1. So f of g of 0, f of g of 0 is equal to 1. Now we do g of f of 0, which is going in a different order. So first we're going to do f of 0. So f of 0 means go to the function f and substitute 0 wherever you see the variable. That's going to give us negative 5. And now you want to do g of negative 5. g of negative 5 is go to the function g, and wherever you see the variable, substitute negative 5. So you're going to substitute negative 5 right there. So you're going to square it and get 25. And 2 minus 25 is negative 23. And so what was that? That's g of f of 0 equals negative 23. Notice that we get different answers when we do the composition in different orders. Remember, if you add two functions or multiply two functions, you can do that in either order because addition and multiplication are commutative. But this operation of composition is not commutative. You do not always get the same value if you reverse the order of the composition. The next thing to talk about is the domain of the composition of two functions. And so what you have to realize is that if you're going to do the composition of two functions, f with g, and so in this example we're doing g first and then f, you can only do the second function in your order of composition if the output here, g of x, is in the domain of f. So you have to be careful about the domain of your functions. You have to be also aware of what the range of g is so that you know whether those values are in the domain of f. So let's look at these examples. Well, for this first pair of functions, f and g, we see that the domain of the function f of x is all real numbers, and the domain of the function g of x is also all real numbers. So if you were to do the composition in either order, f of g or g of f, you would still get all real numbers for the domain. So let's calculate a few of these: f of g, g of f of f, and g of g. Now, we did all these in class, so I'm not going to do all of them, but I'll show you f of g one more time, and I'll show you g of g, I guess. So let's do f of g for the first pair of functions. F of g of x means that you're going to first substitute g of x right here, and so that's going to give us f of g of x is x plus 1. And now that means you're going to substitute x plus 1 into the function f wherever you see the variable x, and there I see it only in one spot. So that means I have to take x plus 1, which is this value, and what does f do? It squares. So I get x plus 1 squared. Now I'll do g of f. G of f of x is, well, again, first substitute f of x right there. So g of f of x is x squared. And so that says, go to the function g, and wherever you see the variable, substitute this expression. Well, here's the variable in the g function, so I'm going to substitute x squared right there. So I have x squared plus 1. So you can see that the domain of this function and that function is all real numbers, because these are just parabolas, and they're defined for all real numbers. Okay, let's look at the second example. F of x is x over x plus 1. G of x is 2x minus 1. So let's calculate f of g first. So let's get a little room here and calculate, get rid of some of this stuff. I'm going to calculate f of g. Okay, so f of g of x means we're going to substitute g of x right there. So we're going to get f of, and g of x is 2x minus 1. All right, and so now we're going to calculate f of 2x minus 1 by substituting 2x minus 1 into the function f wherever we see x. So we have x right there, and we have x right there. I'm going to put 2x minus 1 in those two places. So we get 2x minus 1 over 2x minus 1 plus 1. And when we simplify this, we get 2x minus 1 over 2x. And we see that the domain of this function is all real numbers except x equals 0. Now, the reason x can't be 0 is because 2x is in the denominator, and if x were 0, the denominator would be 0. So the domain of the composition function has actually a couple of restrictions, because f of x must be also defined, and f of x is only defined if x is not equal to negative 1. So you can't even do the composition unless you have that part of your domain. So let's see, the next one I wanted to do is, I did f of g, so I'm going to do, let's do f of f, because I think that was a hard one in class. So we'll do f of f and see how that works. Okay, f of f means, first of all, substitute the function f of x right there. So we're going to get f of x over x plus 1. Now, this means go to the function f and substitute this expression, x over x plus 1, wherever you see the variable. Again, I have to substitute it into those two places. So I'm going to get x over x plus 1 as my numerator, divided by x over x plus 1 plus 1. So you can see that all I've done is I've substituted x over x plus 1 where I used to have x into the f function. Okay, this is a compound fraction, and the way to simplify that is to multiply by 1, and we went over this in class as well. I'm going to write 1 like this because this way of writing 1 allows me to do some fancy canceling here. I have x plus 1 here and I have x plus 1 there, so that's going to reduce to just x in the numerator. And in the denominator, when I have to use the distributive law here. I have to multiply x plus 1 times everything in the denominator. When I multiply by the first, right here, the x plus 1s are going to cancel and leave me with x. And then plus, when I multiply x plus 1 times 1, right here, I end up with x plus 1. And so that gives me x over 2x plus 1. So I see from this that x can't be negative 1/2. So the domain of the composition has to take negative 1/2 out. We did the area of a ripple. So what we found out is that if we drop this stone into the water, it's going to create a ripple that expands outward at a speed of 60 centimeters per second. We did this by looking at a table of values where x is the number of seconds since you dropped the stone, and then g, the function, is the radius in centimeters. Okay, so it's the radius in centimeters of the circle that's created as the splash moves out, sort of the way waves for an underground earthquake would be created and making a tsunami. So if you haven't dropped the stone left, of course there is no circle, so the radius is 0. Let's just use some whole numbers here. If you dropped the stone and 1 second passed, then the radius of that circle will be 60 centimeters because, remember, it's 60 centimeters per second. So after 2 seconds, the radius will be 120 centimeters, and after 3 seconds, the radius will be 180 centimeters. And just for fun, after 3.2 seconds, the radius will be, well, how did we calculate this? We just multiplied the x value times 60, the x value times 60, the x value times 60. So we'll just multiply 3.2 times 60, and that will tell us the radius after 3.2 seconds. And so in general, what's the radius after x seconds? After x seconds, the radius is 60 times x, and that's how you do it. So a function g that models the radius as a function of time, x is measuring time in seconds, and so g of x is equal to 60x is the function that models the radius as a function of time. Now, we now want to find a function f that models the area of the circle as a function of the radius. Well, if the radius of the circle is r, then f of r, the area of the circle, is pi times r squared. Finally, we have to do f of g and decide what that function represents. Well, f of g of x is f of g of x, and that's just f of 60x, and that means go to the function f, and wherever you see the variable, substitute 60x. So the variable in the function f is the letter r, and so we have to substitute 60x where we see r, right there. And so that's going to give us pi times 60x squared, and that can be simplified to 3,600 pi times x squared. And that is the function that tells us the area of the circle after x seconds has elapsed. So it's area as a function of time as opposed to this function, which is area as a function of radius. And that's the difference between those two functions.